So if you show me how to do that.
You've got to turn around.
Yeah.
Check. Look at the screen. What's that? And there. So we're ready to rock and roll.
Excellent, thank you.
You're
That's
welcome.
good. Good man. Thank you very much for looking over Santos. Okay, Dan, I will. Thank you very much, Santos. It's not working at all, is it? Great. Okay. Thank you.
Okay, there is internet.
Yeah, there is no way. It's just that page not going. They're not getting it either.
From
No, they're separately not getting it, so it's not just this unit, you know. So I presume it's just down, is it?
yeah, there's something. I think it's down.
Yeah, it's down.
It's down. It's internet's working. Everything's working.
Yeah, okay.
Yeah, it's just that side.
Yeah, okay.
It's down.
Fine. And the other thing is that was left behind.
Okay, I'll take it to.
Yeah, excellent. Excellent. It's just on here, so.
No worries. Yep.
All right, brilliant.
It's busted. Okay.
All right then. Thank you. Cheers. Thank you. All right, good morning. Morning all. All right, we've got an interesting morning in that your canvas isn't working, my canvas isn't working, so I have no idea what we're going to talk about for the next 2 hours, but I'm sure we'll think of something. The bottom line is that what you are aware of, you should now know the three main sort of dose units that are relevant to you. You should know about effective dose, which is the critically important one. If you're going to remember one of those, remember effective dose. Effective dose is sieverts, and it takes into consideration both the type of radiation, and it takes into consideration the radiosensitivity of the organs that you are irradiating. Okay? If you ever publish a paper or write a paper, effective dose is the only sort of dose you should be using. The exception, perhaps the exception to that, is mean glandular dose in the breast. Because when you x-ray the breast, almost nothing else gets irradiated. Okay, so, and they want to, because in the breast, the glandular part of the breast is the radiosensitive part of the breast, not the fatty tissue. So if you know your mean glandular dose, you almost know your effective dose. There's not much difference, okay? So mean glandular dose, often you see referred to in the literature for breast alone. But the critical things for you guys is effective dose. You know that absorbed dose is the overall sort of dose unit, which is the amount of radiation, the amount of energy, rather, deposited per unit mass. It's useful, and it's grays. The problem is it doesn't consider the type of radiation. You now know that there are X-rays, gamma rays, alpha particles, beta particles, neutron radiation, and so on, different types of radiation. The good news is it back? Okay, thank you. The good news is that for X-rays and gamma rays, that the quality factor is 1. So when you talk about dose equivalent and absorbed dose, you're talking about the same unit and the same value. Dose equivalent took into consideration the type of radiation, but it didn't take into consideration the tissues that were irradiated and the sensitivity of those tissues. As you'll find, there are parts of the body, and we'll talk more about this week and next week, there are parts of the body that are more sensitive to radiation than other parts. The dose equivalent didn't take that into consideration, but effective dose does. So what I'm doing this morning now is just literally going over some of those other units you will encounter. Those 3 are the key ones. Effective dose is the ultimate one that you should be aware of. But I'm going to talk about some of the other ones, which is such things as collective dose, entrance surface dose, and those sorts of things. Yeah, good. So you can see from the top there, other quantities you're going to come in contact with. They're not disagreeing with what we've already talked to. They're sort of complementary, if you like, to what we've already talked to. Collective dose. Now, collective dose is simply a term that allows you to summarize dose to a population of people. So, for example, if I knew the individual doses of individual people within this room over a year and added them all together, that would be the collective dose for this population. Okay. So again, another example. If I know, for example, that in Australia, the average person gets 5 millisieverts of effective dose. Now you know what effective dose means. Each person receives 5 millisieverts of effective dose. If I multiply that up by the 22 million people in Australia, I get the collective dose for the people in Australia. Okay? That's what collective dose is. Now you can say, why is that useful? It is useful because, for example, we know if we look at those figures that in Japan, they're actually delivering much more. If we look at the collective dose figures, we realize that they're delivering much more radiation in Japan than they are possibly in Australia. Now that could be because they're using more radiation per examination, but it could also be because they're using more X-ray examinations per patient and so on. So there's a whole variety of reasons for that. It could be that there is more sort of radon particles in parts of Japan and in Ireland and different other countries compared with Australia. So it gives you a sort of an indication of the overall dose delivered to a group of people. Entrance surface dose is something that I used to use a lot. Basically, it means that if this gentleman came in here for a chest x-ray, okay, rather than simply try and estimate the radiation he might receive from that DAT meter we talked about last week, and I'll come back to that this week, where the DAT meter is attached to the x-ray tube, we could simply put something on his back here. You all showed me very effectively, or a number of you showed me very effectively on Friday how to x-ray someone in the PA position. But you'd x-ray this guy in the PA position, you'd have his center point, and then you would put a little dose unit on that center point, okay? And that would give you the entrance surface dose to that individual for that examination, okay? So the entrance surface dose is literally the dose to the entrance surface of something you're irradiating. By entrance surface, I mean where the x-rays are entering that person. Okay? And that's very useful. I used to find those doses very, very useful because it tells me exactly what this individual is doing. Now, what you should be asking me is, okay, entrance surface dose is useful. How do we relate that to effective dose, which you've just said is most useful? Is that there are conversion factors. Once we know that entrance surface dose, and I know the exposure factors, we then go to a table that allows us to calculate the effective dose. So, and it's a very precise measure. Now, it's as precise as the dosimeter, and we'll talk about dosimeters in a few minutes. Yeah? Yeah.
Because your back is not totally flat, so is that the measurement
Yeah.
from the highest point?
Yeah. No, yeah, and that's absolutely right. You could be, the back, there will be curvature and so on, and it is imperfect. But that's the least of the problems, in a way, because you'll find that the uncertainty of these dosimeters is quite large. Anyway, so that doesn't make that much difference to the bigger thing. But you're absolutely right. We could actually, the trick is you just do it at the entrance surface. At least we can standardize it if it's always at the center point of the entrance surface. Yeah. Dose area product, we talked about this before. If this is your X-ray tube, what we've talked about so far is the patient here and putting a TLD here, or a dosimeter, and we'll talk about that dosimeter in a moment. That's what I just showed you. By the way, again, you could be asking me, doesn't that show on the X-ray? Don't we actually see if we stick a dosimeter on this fellow's back, will that not be visible on the X-ray? The dosimeter is so small, it's only about 5 millimeters in size, and it's very, very thin, probably about 1 or 2 millimeters thin. You don't see it. But we'll talk more about dosimeters in a minute. The dose area product meter is literally built into the housing of the X-ray tube. So it's this chamber, if you like, that we talked about before. Okay, that simply is a sandwich of air. It's measuring ionization. Remember we talked about this, or exposure. It's a sandwich of air that is X-rayed. The air gets ionized. You then work out the resultant charge as a result of those ions that are released. Remember that ions are, you've got these electrons released and then positive ions. Pull those apart. You then can work out the charge across that air, which will be proportional to the radiation, and they can then calculate a dose product value. You notice the term dose, and this is the advantage of it, is dose product area. Okay, so it's dose area product. Okay, so it takes into consideration the dose, that's the radiation leaving the X-ray tube. It takes into consideration the size of the exposure, which is really important. This is a key advantage of the dose area product meter. It takes into consideration, because what I just said to you there, I X-ray this dosimeter, okay, on this fellow's back. If I put a TLD on here, that I could have a field that's only this big, or I could have a field that's this big, okay? But it'll give me the same dose, a very similar dose, apart from backscatter, extra backscatter, but it'll give me similar dose. The TLD doesn't take into consideration the area of the exposure, okay? Whereas a DAT meter, because depending on the radiation and the collimation, you could have this much coming out, or you could have this much coming out, or whatever. the amount of ionizations in there will be proportional to the radiation, but also the area, okay? And that's a key advantage of the dose area product meter. It takes into consideration the area of the structure. So you often get the outputs of this not just in dose units, but you'll get it in something like gray centimeter squared. That will be the unit you'll get out of a dose meter. Or it could be milligray millimeter squared, or some version of that. But you've got a dose value and you've got an area value. Okay? And the mistake that people will make in an exam is you'll put, for some reason, you'll say gray per centimeter squared. That's not what it's saying. It's gray centimeter squared. It's a product, not a division. So don't ever write that down as gray centimeter squared. That doesn't make sense. Okay. Yeah. Yeah. Yeah, yes.
So then, next compare, but obviously have a larger collective dose because they have a larger population.
Yeah, that's true.
If you were to compare them,
Yeah, you should standardize. Yeah, absolutely right. And they do standardize. You're absolutely right. Yeah, yeah.
say if you were to compare them, then why wouldn't you just use the average dose for each individual?
The reason why you don't is because if you have the collective dose, you can then talk about the things like the cancer burden on that society. You know, because you're going to have more people in Japan or wherever. You can then say, well, then the chances of the radiation-induced cancers in Japan are this much higher. Yeah. So you can talk about the impact of the radiation more effectively with collective dose. Okay. And the last one I want to show you is KERMA, kinetic energy released per unit mass. Kinetic energy released per unit mass. And it's often used as an alternative now to exposure in air. You know, we talked about Röntgens and so on. It's often used now as it's replacing that. The bottom line is I'm not too worried about KERMA. You'll see it. But the bottom line is that the unit is the gray, and it's very similar to absorbed dose. So if you know the absorbed dose, you'll know the KERMA. It's almost the same thing. At the energies we're using, not at other energies, but at the energies we're using, you find the KERMA is very similar to the absorbed dose. So everything you know about absorbed dose is relevant to the KERMA, including the unit. Okay. That's units. That's all I can tell you about units, you know. You really, and you will hear all these terms, just work through. If you hear a rad, you'll be able to tell me that it is No, don't worry. Anyone? What is a rad? Anyone can tell me what a rad is? No. Almost. Yes, 1/100th of a gray, which then brings you to the absorbed dose situation. What's a rem? Well done. 1/100th of a sievert, which brings us to the, what is that measuring? Or dose equivalent. Yes, absolutely. So if you see rem, rad, sievert, gray, Röntgen, millirads, so on and so forth, you now should be able to steer your way through all of that stuff. If you see Curie, becquerels, and that sort of stuff, that's different. That's radioactivity. Okay. What we're talking here about is X-ray dose. Okay. And here's just some other features that you may want to be familiar with. Okay. So how do we measure it? So the thing I want to do before the break is just go through the ways of measuring radiation dose. And the first thing to really acknowledge about dosimetry is that it is not a precise science. You think it would, Medical physicists have created these dosimetric sort of materials and equipment, but it's far from as precise as you think it should be. And that I came back, I mentioned that to your question earlier. But we'll look at this in a bit more depth. And if you look at this, there's really three main options, okay? You can measure the dose here, as we talked about. You can measure the dose here, that we talked about. Or you can just get rid of the patient and have some sort of electronic dose meter that you can measure the dose. You know, they're really the three key options. Of course you can estimate. You'll see these factors. Someone brought it up to me at half-time last week about where you can use the KVP and MAS and multiply it together and you get a number. But now you know for sure that using the KVP for anything is a bit of a dodgy activity, you know, in terms of trying to understand what's going on in the beam. So we're really going to look at this one first. We're then going to look at this one, and then we're going to look at just an electronic dose meter that can be simply something as simple as something that looks a bit like an iPhone. You know. So the bottom line is radiation is potentially hazardous. You know that. Every exposure carries a risk. You know that. And measurement is critically important. When we get to diagnostic reference levels, you will, and we mentioned this before, you will realize that there is a legal obligation on us to actually ensure that we do not go above recommended levels of exposure, recommended levels of dose. How can we, if you're managing a department, how can you ever be sure that you are below that level unless you're measuring the dose? Measuring the dose is something that's critically important. It's important for the patient and it's important for you. Now, just to get out of the way, the staff measurement thing, I think I mentioned this in the first class, is that quite rightly, people like you are concerned about, you know, if I'm young, if I'm working in this radiation industry, what is the risk of inducing cancer to me? And that's why you wear those badges, and you should wear those badges and wear them appropriately. But as I say, in all my dealings with students for 2.5 decades, I've never seen a true excessive readable dose on those. I've never seen a readable dose on those dosimeters. In fact, the dose you receive is absolutely tiny. And they can measure, usually those dosimeters can measure down to 0.1 of a millisievert. Okay, those sort of dose, and it varies, it's highly variable. But about 0.1 of a millisievert is a good rule of thumb. And don't forget, just from living this year, you'll receive 50 times that dose. Okay, so you're actually receiving a tiny, or any sort of amount of radiation. It's immeasurable anyway. As I said, the only time that I ever came across, I think I told you this, was one guy came in with a reading, I think it was of 12 millisieverts over a 3-month period. And it turned out that his mates had got his TLD and x-rayed it 1,000 times in the x-ray demo room, and that's how he got his reading. So that's the only measurable dose on a staff TLD I've ever seen, on a student TLD. Okay, so measurement is critically important. First method, thermoluminescent dose meters. Okay, thermoluminescent dose meters. The reason we use that term is you get these little structures. They're usually materials like lithium fluoride, okay? You see that, lithium fluoride, lithium borate. They're tiny, 5 millimeters square. Now you can get powder, you can get a whole load of different types. You get circular ones. Well, the ones I've ever seen are about 5 millimeters square, okay, and about 1 or 2 millimeters thick. They're absolutely tiny. And you x-ray them, you then create excitations within them, which you release. As you can imagine, you're ionizing this thing, you're going to release electrons, okay, that become trapped within the structure. So you ionize the ions within, or you ionize the atoms within the lithium borate, you excite electrons, the electrons get trapped at these higher energies, and then only get released when you heat them hence thermo. You only get heat released when you heat them, and when you heat them, they give off light. They release this excess energy in the form of light, hence luminescence. Okay, so the way that these work, thermoluminescence, you X-ray them, you ionize the atoms, you release electrons, electrons get trapped, you then heat the structure, the electrons have enough energy to come out of their traps and they release light, okay? And you measure the light. So the light is proportional to the number of electrons, which is proportional to the amount of exposure, and that's the way it works, okay? So more light, higher dose. So you've got to calibrate these things, okay? And you've got to calibrate. So say you wanted to do an experiment, how you calibrate them. So basically what you've got the TLDs, then you've got an oven, you put the TLDs into to heat. The oven then heats them, gives you a readout in number of electrons, and then you've got to try and calculate, or else the machine nowadays will calculate for you the dose delivered. Okay, so that's essentially how the thing works. But the problem is, if it says to you, after an exposure, you've X-rayed a patient for an abdomen X-ray, and it says to you 700 or 7,000 light photons. You know, that's how many light photons it's released. What does that mean in terms of dose? Now, the machine may calculate it for you, but if it doesn't, you've got to work it out. And what you do is, before you do any measurements with the TLDs, you maybe get about 10 of them, put them on a dosimeter, okay? Put them on an electronic dosimeter, which I'll come back to. X-ray them, okay, with a known KVP, okay? And then measure the TLD, see the light photons, and then you can equate the light photons to the dose that the dosimeter gives you. So if you see 10,000 light photons and it's saying 10 millisieverts, you know that 1,000 light photons equals 1 millisievert, and that's how it works. It's as simple as that. So that when they talk about calibrating TLDs, all you're doing is you're X-raying your batch of TLDs, 10 or 100 TLDs or whatever. You're reading the dose that's being delivered because you sat them on a dosimeter. So you just sit them on a dosimeter, you X-ray them, you get your reading from the dosimeter, you then put the TLDs into the machine, heat them, get light photons, and then you can equate the light photons with your readout on the dosimeter. Okay, and that's what they mean by calibrate. The critical thing that I said there was at a particular KVP. You calibrate TLDs to a specific TLD. So your exposure of the TLDs on the dosimeter is at 70 kVp. So then you've calibrated them for 70 kVp. Now if you use 60 and 80, that's reasonably acceptable, but they're not acceptable if you're going to use 100 kVp, for example. Okay? So they're calibrated to a particular kVp. In fact, I don't have the word calibration on there, and I should. Calibration is critically important. They don't make sense otherwise. You get a whole load of light photons. You know, what does it mean? So it describes your air Kerma in milligray. Remember the doses that you're likely to receive. And these are used, remember, for entrance surface dose. They're not effective dose. You can calculate effective dose from them, but they're going to give you entrance surface dose. So for entrance surface dose, for this guy's chest, for example, if you did it for a chest PA, you're probably going to get about 0.2 millisievert. I'm going to give you some figures to give you a reasonable understanding of some of the doses. So for a chest PA, you probably get an entrance surface dose of around 0.2 millisieverts. You see, it's easy to remember these. There's not many of them you've got to remember. If you want to go into all the details, there is, but for the, for most examinations, you only need to remember a few numbers. For AP abdomen, AP pelvis, AP lumbar spine, you're probably talking around something around maybe 5 millisieverts. Remember, these are entrance surface doses. Okay. 5 millisieverts. For a lateral spine, lumbar spine particularly, you're talking about 10 to 20. L5S1, you know, the junction between the fifth lumbar vertebra and the sacrum, if you're coming in this way, is probably about 20, a little bit more, 20 to 30 millisieverts. So did you get that? Yep, okay. 20 to 30 millisieverts. And once you have that, you can start working out the rest. You know, once you have that, you know your exposure factors for those sort of things. You can start working out what it would be for a shoulder, or already know a hip. A knee would be a bit less than a hip, and pelvis, and so on. So just to go over these are entrance surface doses. Chest, about 0.2 millisieverts. AP, abdomen, pelvis, lumbar spine, about 5 millisieverts, maybe a little bit more. Then lateral lumbar spine, 10 to 20, L5S1, 20 to 30, and therefore you can roughly work out the rest. You can look these up, but that gives you at least some rule of thumb. Now, when you convert these into effective dose, so all I've done is I've just got the entrance surface dose. Now I've got to work out what organs are being irradiated and how sensitive they are, and that allows me to calculate the effective dose. For chest, the effective dose, well, I'll give you another rule of thumb, and this is a rule of thumb, but the effective dose is often between 1/5 or 1/10 of the entrance surface dose. So now you've got these entrance surface dose figures. If you look at 1/5 of those or 1/10 of those, you're going to be close to effective dose figures. And they're the important ones. Because then you can say to the woman coming in, when she asks, my 7-year-old boy is having an abdomen x-ray, or he's broken his hips, or he's got dislocated hips, and he's having regular hip x-rays, he says, my God, what's the risk of this x-ray? And that's a perfectly legitimate question. Now you can start thinking, okay, hips, okay, this is an adult hip would be an an effective dose of probably around 1 millisievert, roughly, 1 millisievert. Okay, this is a young boy, so I'm probably giving about half of the MAS, so I'm probably giving it 0.5 millisieverts, okay, effective dose. That's the first half of the equation. Once you can do that, you can then work out the impact of that radiation, and I'll be giving you the information over the next 2 weeks how you actually work out the impact of the radiation. But that's the first half of the equation. Once you know the dose that you're delivering, without that, you haven't got a chance. Yeah, you had a question, I think, yeah.
That's right. You semi-answered it.
Okay, fine. Okay, sorry, yeah.
Sorry, can I just check the brain? Effective dose is usually 1/5 to 1/10 or?
It could be, it depends where you're irradiating, you see. So I would have thought around somewhere between 1/5 and 1/10. It's a very rough rule of thumb, but at least that's more useful than having nothing at all. Yeah. Yeah, you see, the problem is there's not very much. When you look at all the studies that are done on doses, it's usually about the torso, and it's usually often involving CT and as well as general X-ray. There's not a lot for limbs because they're far less radiosensitive. You're away from the vital organs, although the bone marrow's there. You're often away from the really radiosensitive parts of the body. But the doses from those we can roughly calculate. For an elbow, for example, and I'm simply just thinking, you give an elbow probably around 5 MAS and 60 kVp. If you can think that for an abdomen, you probably give around 65 kVp and 20 MAS. So you talk about 1/5 of that sort of exposure. So then so we said 5 millisieverts for an abdomen. I'd be talking maybe 0.5 to 1 millisieverts, and that's entrance surface dose for an elbow, for example, or for a knee would be a bit more than that. So we can, at least it gives us an indication, Okay. All right. Now, just to go over these TLDs, Aircomb and Milligray, they're not useful for fluoroscopic examinations. And if you think about that, that makes sense. For this guy's chest, it's easy. He's there, we put it on, we X-ray and we take it off and we get a dose. For a barium swallow, if we put it on here, for example, For some of the exposure, it's going to be out of the beam. Other part of the exposure is going to be in the beam, then out of the beam, then partially in the beam, and so on. For a fluoroscopic exam, and some of the X-rays will have traveled down to the stomach at that stage because we'll have moved the X-ray tube. We'll be missing the TLD here. So for fluoroscopic examinations, unless you put loads of them on, it's of no use. You know, the fluoroscopic examinations, we wouldn't use TLDs for. And this is where the dose area product becomes really important for fluoroscopic examinations. Lithium fluoride, lithium borate they're made of. We add copper manganese to them to make them more sensitive. The problem we did pediatric dose levels in Ireland 10, 15 years ago. And one of the problems we found was the TLDs weren't picking up so we had 5-year-old children coming in. We put the TLD on, we're getting no reading, you know, because they weren't picking up those lower doses. So what we had to do, we had a choice. Use the TLD for several patients to build exposure up and then average it, which is a bit crude. Or else you can get these copper manganese doped TLDs, which lower or increase the range of exposures that the TLD would read, and it gets you down to much lower levels. So it increases the sensitivity of the TLDs. You always put TLDs in a little sachet. So even though they're these tiny TLD things, you devote a sachet to them. Now the sachet is like a piece of plastic. And what it does is, if you put the TLD on his back again, the layer of skin at his back is dead. The outer layer of skin that we've got is actually the stratum corneum, and it's dead. You know, it just doesn't live. So what you're effectively measuring is the dose to this dead layer of skin, which makes no sense because it's not relevant. You want to get in a little bit with the dose to find out what the dose is to the living tissue. And so therefore, by putting them in the sachet, that sachet simulates the dead layer of skin. So what the dosimeter will receive is something that's closer to the living layer of skin. Okay. I saw a very interesting fact, which is completely irrelevant, but I thought it was quite humorous or interesting recently, that we know that when we weigh ourselves or whatever, we get a weight, that 48% of us is actually human. You know, the rest of us are made up of microbes and bacteria and so on. So only 48% of us, what you see here, is actually human. Anyway, that's fine. Completely irrelevant, I know. Okay, so what we're trying to do is absorb dose to air at the skin surface. That's what we're actually measuring. Now, this is critically important. Now, this is one of the key advantages of a TLD. A TLD will measure backscatter. Now, what do I mean by backscatter? You put the TLD on here. So what dose does this skin receive, for example, or the air just adjacent to the skin receive? It will receive the dose coming down, but then all the X-rays will be interacting here, and some of them will backscatter in this direction and upwards and around and so on. The TLD will measure that backscatter, and it will increase the reading levels by about 40%. Okay? So it's an important feature of your exposure, of your dose delivered, that a TLD will capture. That a DAT meter will never capture because it's too far away from the patient. The DAT meter will never capture that backscattered radiation. Yep.
Sorry, if it's very, very small, how exactly is it capturing all of that?
Well, it's capturing it in that unit. The TLD, remember that absorbed dose is per unit mass, so it's actually just measuring what that. It's not measuring all the backscatter, but at least it's measuring the backscatter at that point, and it will increase the dose at that point by about 40%. Size and cost. The reason why we used to use a lot of them is because they're cheap. They used to be about $1 or $2. I think they're about $10 now per TLD. So they're cheap, and they're small, and so on. The problem is they are inconvenient. They are inconvenient. Whilst I really like, if you're going to do an experiment and want to know the dose to something, I really like them if you can use them, because they tell me exactly what this dose is at this person's entrance surface. Then I can calculate the effective dose. The problem is you've got to then take them, you've got to read them. The whole reading procedure, it used to be one at a time, now you can read 50 at a time, and you get your values and stuff, but there's a whole load of other stuff. You've got to calibrate them. They're inconvenient, but I still like them. They are pretty useful tools, but very rarely used. I'm sure you probably won't see any in your training because they are inconvenient. Oh yeah, there's calibration. Calibration I've talked about. Reading, I've talked about. Basically, you've got to put these things into an oven. They heat the thing. You get light photons and so on. Some of the latest ones don't need heat. They can be simply stimulated with light. Okay, but there are lots of inaccuracies with TLDs, and it's again coming back to this point here I raised here. The first point is when you X-ray it, okay, and you measure it within seconds. We had a student who did this experiment, and she was X-raying in the X-ray room and then literally sprinting to the reader to try and minimize the time gap between exposure and reading. But when that gap increases, you get this thing called TLD fade. It doesn't hold on to all the information. Okay, so you X-ray. If you X-ray something and can measure it within a minute, you'll get a slightly different reading than if you measure it in 10 minutes or 20 minutes. So if I X-ray this guy, the best thing I can do is get this TLD read straight away. But I may have 30 other patients waiting, so I may have to wait till this afternoon before I can read these TLDs, and that can cause image fade, which is an issue. The TLD reader can vary. That oven that I talked about, it can vary in terms of light outputs and amount of heat it applies and so on. They can demonstrate a non-linear response. So in other words, 10,000 light photons compared with 5,000 light photons doesn't necessarily mean twice the dose. Okay, so you've got that sort of variation going on. This is back to calibration. Beam energy dependence. Remember, it works at a particular kVp. And you can see the level of uncertainty there. You've got 25% uncertainty at that range of doses and at that beam energy. Okay. The next one, and again, you know most of this at this stage, is DAP meters. These dose area product meters. Basically an ionization meter. They just literally, you've got a sandwich of air, you're X-raying it, you're ionizing the air. Your output's a gray centimeter squared. It's attached to the X-ray unit. And you usually get an instant display. Now that display can be on the unit, it can be on your X-ray unit, and it can also be embedded within your DICOM header. I don't know if you've come across DICOM headers yet, but your image, when you produce a digital image, it has a whole host of other information housed within it, so it can recognize that it was this woman's X-ray, and her ID will be on it, and so the exposure factors will be on it, but it also will often have the dose value on it as well. So all that information can be fed into the system. Does not measure backscatter, that's a problem. It does work for complex examinations. That's a good thing. So if you're doing an angio, for example, regardless of what part of the body you're looking at and what position the patient is at and what movement's going on, it will capture everything because it's taking everything that's leaving the X-ray tube. And we'll talk about DRL measurements in a couple of weeks, but really this is the way that diagnostic reference levels are going to be used. Now, I think there are, as I said to you before, advantages with TLDs, but there's no way you're going to get people, they're inconvenient. You're not going to get people to use these TLDs all the time because they need to calibrate them, they need to put them on, they need to make sure that this TLD is not reused on this guy, they need to then bring it to the reader, they've got to read it, The reader needs calibration as well. Too messy, so you'll find that people will go for the easiest options, and these are much easier. The DAP meter option is much easier. The last method that I want to talk about is electronic dose meters. And these are simply devices, like an iPhone. You know, you can buy them. They're now got very small and neat. They used to be big, hefty things. They're now small. Basically, you X-ray this, and it tells you the dose. Okay? So it's just simply, it's expensive. The dose value is immediately available. Its accuracy, again, comparable to what we've seen earlier. You know, the Geiger counters. You ever see these old sci-fi pictures, you know, where people, and you still get these, where you've got this tube and you go over to a woman, it starts crackling, you know. That was the old-fashioned sort of, and they still have them, the old-fashioned sort of electronic dose meter. That was known as a Geiger counter, okay. But they're now sort of semiconductor diodes. They store and display the results. But they're very convenient. They're very, very handy. You know, you just get it. You say, I want to see, if I gave 23 and I gave, if I gave 70 kVp and 23 MAS, what dose would I receive? Or what dose would be delivered compared with another exposure? It gives you an instant readout. You can X-ray away, okay? The problem is you can never use it with patients. You can't stick this thing on someone's chest and X-ray it, you know, because you're obviously going to see that on the image. So there are limitations with it, but for quick, rapid, consistency experiments, they are really, really useful. They're also necessary for calibrating TLDs and such like. Large dose range, 1 microsievert to 1 sievert, and large energy. They can tolerate large energy ranges as well. But these aren't inexpensive. You know, they could be about maybe 40, 50, 70,000 for decent dose meters. You know, they are reasonably expensive. All right, so they're sort of the 3 main groups of dosimeters that you need to be considering. The DAP meter is really where you're going to go. That's going to be the unit you're going to see most of. Okay, any questions or queries? Okay, so that's doses sorted. When you come after the break, we're going to kick off a little bit about the effects of radiation on man. We're going to sort of do a bit of the background after the break, and then next week we sort of get into the interesting sort of biology and some of the risk factors and so on. Okay, it's now, I reckon, it's now 10:54. If we come back at 5 past. Hey. Yeah.
You mentioned backscatter.
Yeah.
Is that good for the measurement or bad for the measurement?
It's good for the measurement because you're capturing at this point. You want to know what radiation is being delivered.
Yeah.
Okay. Some of that radiation is this coming down. Okay. But some of that radiation is backscatter. So if you don't get the backscatter, you're not getting all the radiation, you're not getting a true informed amount.
But the backscatter is, the backscatter is from the tissue. Then it's bound back.
Yeah.
So,
But it's still an effective radiation.
yeah, but it's already measured.
No, but what we're trying to do is we're trying to measure the effect of that radiation. You may have measured it down here or down here somewhere with other TLDs, but you want to know that piece of tissue there, how much radiation is it receiving? You know, and therefore you need to know what's going forward, and any radiation then that's bouncing back, what is the total amount of radiation that piece of tissue is receiving? And to do that, you've got to have backscatter.
okay, so seriously. But, and another question.
Yeah.
For the millisieverts, I think I'm asking you in the email and asking if it's just the probability or the ability for an X-ray to analyze things like.
Yeah.
So it may be just a bit, but what if like all the air in the
DAP meter, yeah.
meter being ionized, then after that the if it's limited, after that it will give you.
Exhausted of. It doesn't work like that. What happens is eventually those electrons, there's loads of free electrons and stuff in there. So all the air and stuff is going to reform, if you like. The electrons are going to reform onto the ionized air.
I mean, it will reform. After one shot, it will give you current.
Yeah, it will give you current.
Yeah, but what if all the air be ionized and it be a hot light? The nuclear, the nuclear and the electron part away, or I know it will give the current mass of energy, but what if it's that? Then
It still would work. It still the ionize. You can use it. I know you can use a DAP meter for 20 years. You know, so it's not going to run out of. It's not going to run out of electrons.
And I know it's the ability of the X-ray to ionize things.
Yeah.
But is that relative? Because the atomic number of the air is quite different from our tissue.
Yeah.
So, and for the ionize, we need to know the band energy.
Yeah. And you'll actually find that the ionization of air is sometimes not as different from, and I do cover this in my book, it's not that different from the ionization of tissue or liquid. It's not as different. It is different because in lungs we get a lot of blackness compared with the abdomen and stuff. It is different, but not as different as you'd imagine. But that is all taken into one of the weaknesses of the DAP.
I just want to know if it's just the probability we mentioned is one photon will hit one electron, and because the atomic number of the tissue and the air is too low, so basically each photon hit an electron will release it.
Yes. Yeah. Now we're going to talk more immediately after the break about the interactions of X-rays with tissue.
So
we're going to see that.
Every photon will release an electron.
Not every photon. Every photon interacting with an electron will release an electron as long as that photon's energy exceeds the binding energy of the electron.
Yeah, I see. If all the photon from the X-ray can release an electron in our brain, like on the tissue, why hit it? Why interact it?
Okay. Well, I'm going to talk about this after the break.
Okay.
And if you've still got the same question, come back to me, because hopefully we'll address it after the break. Because I'm going to talk, the primary aim of the first half an hour after the break is to talk just about what you're talking about, the interaction of photons
And then another
with
thing,
tissues.
if the photon enters too high, it will be absorbed a bit.
Yeah, it will. Oh yeah, you'll definitely get some absorption between here and here. There'll be some absorption, but it's not a lot. It's not a lot.
What if when we release the electron, electron will absorb the energy of the photon, and it will be transformed to maybe hit a bit, and another will transform to the kinetic energy of the electron.
Yeah, and that kinetic energy of the electron can cause biological effects, which again we're going to cover next week when we talk about the.
When I do the research, I recommend something called the gamma H2AX.
Yeah. Okay. Yeah. I'm not. I'm not convinced of that formula.
Is that the kind of chemical we measure for the double-strand protein?
There are methods. It's a variety of different methods. Normally with DNA strand breaks, we have this thing called electrophoresis, which can allow us to measure how many strand breaks are in a particular collection of cells. Yeah. But we will come back to some of this next week. Okay, good man. Yeah.
Really simple question.
No, that's all right. That's okay.
We're wearing.
The which?
The
Yeah.
So what concept is that?
That would be. It used to be film.
Right.
It used to be film.
Okay.
Now it's just literally the blackness of film. And it used to have a fast edge and a slow edge. So if you got a load of dose, you had a slow emulsion that could still measure by the. And film, surprisingly, is still used in radiation therapy to understand the doses that people are getting. How black it is, then you got more a dose. Most of it till recently was TLDs. So you'll actually be using thermoluminescent dosimeter characteristics.
What about the phase though? If we're 6 weeks.
Yeah.
Surely.
Oh no, yeah. But the fade, yeah. I know you said the fade is there, but it's not. It's for the solid dose you're going to see. It's going to make no difference. Really, very, very little difference. In fact, that could be an experiment. Give exactly the same dose, and then get your TLD, hold it for a day. Someone else's that had you wear 2 or 3 TLDs, and do it, and then read one after a day. Read when at the end of the 3 months, read one after a day, after a month, after a year, or whatever.
So do they use those results for anything, or is it just like a...
No, it's really a statistically, it's just obligatory. And I think they probably help. They probably use it to help calculate your annual doses. So if you're a
In the
fairly
real world,
typical
no
person,
radiographers actually wear them, do they?
don't they?
I don't know.
Oh, they should. They should. I think they do. Yeah.
Oh,
they
so
do.
everyone has to wear
Oh no, I think it's obligatory that
I thought
they
it
do.
was just maybe like
No, no, we don't inflict it on you. No, I think everyone sort of everyone wears them
hand them in
every 3 months or whatever. Now, some of the newer ones are these optical stimulated dose inhibitors. Find out which ones. Your person giving you the TLD should be able to say what is the technology, but I would imagine it's either TLDs. Okay, and whoever gave them to you, ask them, is it TLDs or is it optical stimulated dose inhibitors, Yeah. All right, okay, right then.
I just sort of overall think like the electron, or no, the photon hit the electron and release the electron,
Yeah.
and if we consider assume 100% photon, 100% of photon which is interacting with the electron
Yeah.
will release the electron
Yeah.
and pass through our body.
Yeah.
Okay. Then in X-ray, but some photon will just be back.
Yeah. Some photons will come back. Some photons will continue, and some photons will bounce back. But most of them will be in a forward direction. Well, that depends largely on your KVP, your energy.
Yeah, the energy. But the energy will give us the wavelength of the photon.
Yeah.
And the wavelength of the photon will give us the ability of it to analyze if it can analyze an electron.
Yeah.
So what if actually if the photon has a lower energy, it will be faster.
Yeah. It's more likely to, if a photon, it depends on a number of things, but I think it's hard to know. I would have thought a low energy photon is more likely to be absorbed.
Oh yeah.
A higher energy photon is more likely to be scattered, and so you're probably going to get more backscatter with high energy X-rays.
Yeah. And but the dose, in anything one we consider about the dose is the ability of it to analyze things.
Yeah.
I just do some research about and lower dose effect on our body. That's why we do that. And let's say the repair.
Yeah.
The repair of the DNA will be harder than the repair of the DNA with a higher dose.
No, not necessarily. It depends on the type of dose. It depends on the type of ionizations that happen within a particular exposure. It's not so much on the dose. It's on the different, if it's a double strand break or if it's a single strand break. That's much more important about repair than the dose. But you're probably going to get, if a higher dose, you're going to have more opportunities for double strand breaks, admittedly. Yeah.
Yeah, but on the research side, for low dose, the double strand protein is hardly to being repaired.
Correct.
Than a higher dose. Wow.
Why is double strand breaks harder to repair?
The double strand harder to repair for a low dose than a higher dose. Higher dose.
No.
Other research just say the higher dose, the the double strand broken after higher dose DNA is either repaired than a lower dose broken.
No, I think a single strand break, a single double strand break, okay, it's irrelevant what dose it received. It will have the same amount of ability to repair whether it was hit by with high dose or low dose. But with high dose, you're going to have more strand breaks to repair. But for one double strand break, the dose doesn't matter. For one double strand break, the dose doesn't matter. It'll have the same ability or not to repair.
And I just consider about it's a dose rate because I see lots of things mention dose rate. Is it dose rate?
Dose rate.
Yeah, dose rate.
Yeah, that's important. And I'm going to talk about that next week in radiobiology.
Okay.
Yeah. Hi. Yeah.
Would you say the measurement is non-linear to
Yeah. Linear. Yeah.
linear? Yeah. But this one, DAP, you measure the kind of the exposure.
Yeah.
To
Ionization. Yeah.
the ionization around the windows.
Yeah.
It's linear.
It's more
response
linear.
to
It's more linear than the TLDs. Yeah, it is. Yeah.
more linear to the KVP and the mass.
No, it's more linear to the dose, to the amount of ionization. So, if you get twice as much radiation being emitted from the X-ray tube, you'll get twice the reading on the DAP meter.
Okay.
Yeah.
So the reading is corresponding to the exposure dose, but like we want to reduce like half the exposure.
Yeah.
How can we adjust the KVP and the mass?
Okay. Just the MAS.
Just a mass.
If you just want to half the exposure, half the MAS. KVP is really tricky because it's KVP squared. Yeah, it's not linear. Yeah. How's your head? Is it good? Okay, good. Oh. Yeah, okay, right there. All right, let's continue. All right, so what we're going to talk about for the next half an hour or so is, before we get into radiobiology, we've got to just go through the interactions that occur at the atomic level, because what I want to try and explain to you so you understand it from the sort of whole picture is over this week and next, what I'm going to try and explain to you is the effects of radiation at the atomic level, then bring it to the molecular level, then we'll bring it to the cellular level, to the tissue level, and then we'll eventually talk about what does this mean if you deliver a dose to a child or to an adult or whatever in terms of induction of cancer, and also deterministic effects, which we've talked less about. So I wanted to bring you through that whole passageway. So you need to understand sort of the atomic level stuff before you understand the molecular, the cellular, and so on. We'll also talk a little bit about why certain tissues are more sensitive than others. You know, why is breast tissue much more sensitive than skin tissue, for example? You know, why is the lining of the small intestine very sensitive to radiation, whereas the muscle of the small intestine isn't? You know, why do people get sick after radiation therapy, for example? So we'll go through all those things, and at the end of it, you'll have a full understanding, or at least a good understanding of why radiation is hazardous and the sort of effects that it can actually create. But before we do that, what I want to do for the remaining part of today is simply go through the interactions of radiation, okay, and particularly talk about the atomic level interactions. And to do that, we've got to go through two different processes. I'll just try and clean this if I can. Okay, so there are two key processes. Now, I said to you before, be alert right now, because this is the second of the interaction processes which you could be asked for to describe in the exam. Remember, there's the initial interaction process within the X-ray tube, where you have the X-ray tube and you have the electrons interacting with the anode. And we've talked about that. We've talked about Brandstrahl and we've talked about characteristic radiation. That's the first interaction question you could get. The second interaction question you could get is now when the X-rays emerge, what are the interactions within human tissue? That's what we're talking about now. So if you see the word interactions, please be careful and read the whole question. Because if that question comes up, there will be at least 3 or 4 of you that will answer the wrong thing. You will give me the other interactions. So beware to make sure and sort of read the whole question. All right. 2 processes occur. So we're talking about what happens here when the X-rays interact with the human body. And 2 processes do occur. Photoelectric absorption and Compton scattering. You can see the opportunities for confusion, because with the other interaction process, there are 2 events that occur also, you know. So do try and separate these out. Remember that the X-ray is chargeless. Okay, it has no charge. An X-ray has no mass. It's simply energy. An X-ray has no charge. It has no mass. That's why it works. If it had charge or if it had mass, it wouldn't get through the body so effectively. Okay? So this is why we use X-rays for transmission imaging, is that because it will pass through the body and only interact with certain things. So the X-ray is going to interact with the atoms within here. So you've got an X-ray coming in, and then you've got atoms of different molecules within the body. Okay. What is it likely? Just you can work it out again. You know, remember we did this before with the other process. What is it likely to hit? What is the most likely thing that incoming X-ray is going to hit? Electron. Yeah, it's going to hit an electron. Now, you may be tempted to say, and it could hit a nucleus, you know, like we talked about before. It won't hit a nucleus. Not at the energies that we're talking about. That's not relevant. So the nucleus for this thing, you can rule out, okay? It's not going to hit a nucleus, okay? But it will hit an electron. Particularly the more electrons there, the more likely it is to hit something. So it'll hit the electron. Tell me what happens next. It's going to hit an electron. What's going to happen? It could kick out this electron if The energy is greater than the binding energy of these materials. Now, remember that the binding energy is far lower with biological materials. Okay? We're not talking about tungsten here. None of us are made of tungsten. Okay? We're talking about carbon. We're talking about hydrogen. We're talking about oxygen. We're talking about calcium, you know? Even if you look at calcium, which is one of the highest atomic numbers in the body, it has an atomic number of 20, and yet the K age is only 4. Remember, with tungsten, the K age was 59. Okay. Or 69, in fact. Sorry, 69. So with these biological materials, you're talking about much lower binding energies. Okay. So with calcium, the binding energy of K is 4. For the L shell is about 0.4. Okay. So we're talking about much lesser. Just keep that in mind. Okay, so the likely target is an electron, and if the X-ray interacts with this electron, it's likely to kick it out because the binding energy is so small. Okay, so two things can happen: either photoelectric absorption or Compton scattering. Both of these involve X-rays interacting with electrons. Okay, so that's easy. Both of them involve X-rays interacting with electrons. But let's go into the sort of differences between these two. Okay, photoelectric absorption. So if you're asked to talk about the two characteristics or the two interaction processes when X-rays interact with the body, you're going to talk about photoelectric absorption, you're going to talk about Compton scattering. With photoelectric absorption, you're talking about the lower energies within the X-ray beam. And you're talking about, and it should be right up there, but it's not, you're talking about inner shell electrons. So you're really talking about K-shell electrons. Remember, yeah, I'll come back to that. You're talking about K-shell electrons. Okay, so the critical thing here is in the term photoelectric absorption. When that photon interacts with the electron, it loses almost all its energy. It's absorbed. Okay, it's not scattered. It's not partially absorbed. Well, it can be slightly partially absorbed, but it's generally it loses almost all its energy. If not all its energy, all its energy. So the X-ray comes in, interacts with this electron, loses the energy required to kick this electron out, okay, and therefore you have now the complete absorption of that photon of energy. Okay. The electron is ejected at what energy? If the photon is completely absorbed, what energy does the electron have? Minus. Well done, absolutely right. Basically, if it's transferring all its energy to this electron, okay, this ejected electron will have all that photon energy minus the binding energy it was needed to, the energy equal to the binding energy necessary to get this electron out. So the ejected electron has an energy equal to the photon energy minus the binding energy of the electron. And that makes sense. It happens locally, it happens at that point, and it's more likely to happen at the inner shells, because the inner shells are going to have slightly higher energies, binding energies, that will be relevant to the incoming X-ray energy. Any questions on that? And there's this thing that's almost, for your purposes, for our purposes, is irrelevant, that the atom actually loses a little bit of energy, it recoils slightly to make all the energy transfer balance. Okay, but you don't have to worry too much about that. So the critical thing here, and the thing if you're asked to talk about this, you're talking about low energy X-rays, you're talking about inner shell electrons, you're talking about total absorption. That's why you see bone on an X-ray. That's why you see the heart on an X-ray, is because lots of photoelectric absorption has occurred at that point, which stops the X-rays, and therefore you get a white appearance on the image. Okay? Photoelectric absorption is what makes the image useful. Okay. What we should say, and this is going to be quite interesting to you and useful to you, and support some of the things that you said last Friday in the X-ray room, is that the chance of photoelectric absorption is proportional. So photoelectric absorption is proportional to the atomic number cubed. That's the chances. Because remember when you X-ray someone, I'll let you get that down first. So photoelectric absorption is proportional to the atomic number cubed. Remember when you X-ray someone, you're going to have a plethora of tissues that you're X-raying, with different KAGs, atomic numbers, and so on. You're going to have a plethora of energies of X-rays. You know the sort of Brent Stralum curve. You know you've got low energies, you've got high energies, and so on. So the photoelectric absorption and Compton scattering are all going to happen at the same time. Okay? But the critical thing is that photoelectric absorption, the chance of this happening over Compton scatter is proportional to the atomic number cubed. Okay. So let me explain what I mean by that. Okay. And this is really, really important in terms of image formation. Supposing you have got a bone in there, and I'm going to simplify this. Say the average atomic number of that bone, which is nonsense, but say it was 4. And the average atomic number of the surrounding tissue was 2. Okay? Now, the contrast there is, the difference between that atomic number and that atomic number is obviously that's twice as high as this one. But we're saying the level of absorption is proportional to the atomic number cubed. So the level of absorption that will occur here will be 4 by 4 by 4 in this region. And in this region, it'll be 2 by 2 by 2. Multiply that up, that comes 64, that equals 8. So now the difference of absorption is no longer 2, it's 8. What photoelectric absorption has really cleverly done is amplify your contrast hugely, because it's proportional to the atomic number cubed. And this is why, and I'll come back to that point in a second, but the critical point is that if you can promote photoelectric absorption every time you X-ray someone, you're going to amplify the contrast of the image, because you've suddenly changed the difference from being 2 times by simply the atomic structures to 8 times in terms of image contrast, okay, when photoelectric absorption occurs. And to promote photoelectric absorption, so what I'm saying here is contrast is enhanced, okay? To promote photoelectric absorption, you use lower energies. That's the physical reason why KVPs, lower KVPs, gives you higher contrast. That's the reason why lower KVPs gives you higher contrast, because you're promoting photoelectric absorption, you're promoting this wonderful sort of interaction here that will increase the contrast, and that's critically important. That's really the fundamental principle of why you can decide the image contrast by the energies that you select on your X-ray tube. So anyone who tells you that increasing KVP increases contrast are completely wrong. It's wrong. Reducing energies increase contrast, and there's the reason for it. Okay, any questions on that? And that's the first interaction process. So let's just go over that again. Low energies, inner shell electron, complete absorption, and it amplifies contrast. They're the key points about photoelectric absorption. Okay. Moving, and that's good. That's what you want. Every time you X-ray someone, that's what you're trying to promote. You're trying to get that total absorption in the parts of the body that you want to see. Okay. The alternative is Compton scattering, and you all know that as scattering radiation. You've talked about scattering radiation. Remember that lead aprons are designed not to absorb primary radiation. They're only there to absorb, and you know they only do it so well, they're only there to absorb secondary radiation. You should never use a lead apron to protect you if you've got your arm in the beam or something. You know, that's not there for primary protection. It's there to protect you from the scatter radiation, which is down to Compton scattering. Okay, and it's the opposite. Compton scattering is the opposite. So don't look at the slide. Don't look at the slide. Tell me what sort of energy we're going to do with Compton scattering. Don't look at the slide. Higher energy. Higher energy. Inner shell or outer shell electron? Do you think it's the opposite? Outer shell. So it's higher energy. It's an outer shell electron. We have little absorption, but we do get scattering of the photon. Okay? And that's the distinction between this process and the previous one. So higher energies, the incoming photon interacts with the outer shell electron. Remember that the binding energy of the outer shell electron is low, so any energy, any photon interacting with that outer shell electron, there's going to be a huge difference between the incoming energy of the X-ray and the binding energy of the outer shell electron. So this photon is going to continue moving, but in an altered direction. That's scattered radiation, and scattered radiation is always bad. Scattered radiation, you'll see some justifications from it, just ignore them. Scattered radiation is always detrimental to the image. It's never good to the image. For example, if you've got a structure here, you want the information on the detector to be here for that structure. You don't want any scattered radiation about that structure reaching that way or that way. It only reduces what should have been here, and it enhances what should have been here, so you get reduced contrast. Because this should have been really white, and this should have been really black. But if you get the what happens is that what should have happened here happens out here, and therefore you get a dilution of the difference between here and the outside areas. Okay. So the big difference here in energies is between the incoming X-ray photon and the electron that it's interacting with, particularly the outer shell electron. The amount of Compton scattering that occurs is very dependent on the number of electrons, not so much the atomic number. The atomic number is not relevant or as relevant in Compton scattering as it is with photoelectric absorption. But the number of electrons is critically relevant to the amount of to the amount of Compton scattering that can occur. And that's just a formula that allows you to calculate the number of electrons in any structure. So if you want to count the number of electrons in any structure, you've got N, which is Avogadro's number, with atomic number over atomic mass. With Compton scattering, what happens is it interacts with this outer shell electron, but then the photon will continue as scattered radiation, and this electron will continue, and that electron is known as a recoil electron. I should have said, for photoelectric absorption, this electron is known as a photoelectron. Okay? So this electron with photoelectric absorption is known as a photoelectron. This one is known as a recoil electron. And it's not dependent on atomic number, so you don't get any of this magical stuff that you do with photoelectric absorption. Yeah.
Sorry, can you just with photoelectric absorption, when that low energy comes and hits the inner shell electron?
Yeah.
And what happens with that?
Okay. With photoelectric absorption, the X-ray comes in. The X-ray is going to have a reasonably close energy compared with this. It's going to interact with this, okay, but it's going to give all its energy to this interaction process. So this will be kicked out, but the energy that this has will consist of the original energy minus any energy expended trying to get over the binding energy, okay? But the important point is that this photon of energy will be absorbed here. It will stop here. It won't do any sort of bouncing off like we can see here. Does that answer your question? Yeah. Yep.
So just quickly, are you saying that the energy that's kicked out is called a photoelectron?
In the photoelectric absorption, it's called a photoelectron. Yeah, yeah. The electron is called a photoelectron. The one that's bounced out. Yeah, so this electron, so this electron which is bounced out to here, say, is known as a photoelectron. Yeah.
So with the Compton scattering, that X-ray beam that's now been diverted, who's to say that can't hit an inner shell electron from the next atom along and be absorbed?
Yeah, but you're absolutely right. That could happen. But what you'll get with that then is you will get absorbed dose happening within the patient at that point that contributes just nothing useful to the image whatsoever. Okay. Yeah. Yeah. Yep.
So when you knock out that inner shell electron, I'm assuming you have the same effects that you have in that.
You're on dangerous territory here now because you don't try and confuse them, but yeah.
Yeah, but you've got one K shell electron now.
Yeah.
So you still have an L shell.
Move into its place. Absolutely.
Just the energy differential between those, so that would give standard effect as well.
Completely right. That's absolutely right. If we wanted to fulfill the story, it's not relevant for our understanding of this, but if we wanted to complete the story, what would happen? They've got a space here. This is to move into its position. And you'll get a little bit of characteristic radiation released. But that is, say, if it's calcium, which is one of the highest atomic numbers, you're going to get a difference of something like 3.6 keV, which is never going to leave the patient. Yeah. Any questions on that? Yeah.
So if the electron that is displaced is called a photoelectric electron, then
Photoelectron, yeah.
which one becomes the recoil electron?
The recoil electron is to do with this second process. So the first process is photoelectric absorption. The name gives it to you in a way. Photoelectric absorption, you get a photoelectron. With Compton scattering, you just got this electron bounced off, which you simply call a recoil. It's just really it's just names that they give to this, but the recoil electron is a Compton scattering output, yeah.
Could interactions happen in the same atom?
Can the same, yeah, it could, yeah. Yeah, it could. It could. As long as your atom has more than a K shell. Yeah. But these processes, every time you X-ray someone, it's not a case of you sort of having an X-ray that's just photoelectric absorption, and then you turn up the KVP and you just got Compton scattering. These processes will happen at the same time. What you're trying to do is promote photoelectric absorption, And to promote photoelectric absorption, you use lower energies. Okay. Yeah.
The lower energy promotes absorption again?
Yeah, promotes absorption. Okay, so do you mean this bit?
Yeah.
Okay, you want to go through that? Okay, for sure. And this is probably the most interesting part of all of this. Since we know that photoelectric absorption is proportional to the atomic number cubed, it means that if you've got a structure here, and this has got, I'm just going to use the same numbers, this has got a value of 4, and this has got a value of 2 in terms of atomic number. Now that's highly simplistic, but it gives the picture, okay? And the X-rays interact with this. If photoelectric absorption predominates, the amount of absorption you will see here, proportional to here, is 4 by 4 by 4, which gives you 64, okay? Here, it's 2 by 2 by 2, which gives you 8. So 64 over 8 now gives you a relative difference in the absorption of 8 times, even though the atomic number was only twice. Because Compton doesn't have that ability to recognize the atomic number, you don't get that effect with Comptons at all. Okay? You only get this effect with the photoelectric absorption, because it's really cool. But what it does is it takes these differences within the body, and it has the ability of amplifying those differences. Therefore, we can see differences between a tumor and normal tissue much more clearly if we predominantly use photoelectric absorption. And that's why in mammography we use a KVP of usually around 20 or 30 to try and amplify those tiny differences that exist, as opposed to what we would use in general radiography.
Yeah, I didn't quite get that, because the proportion is proportional to the atomic number.
Yeah.
So it's quite like related to the body itself, the structure inside. But the KVP, the energy. The energy is the outside the outcome, but why the lower energy can amplify the
Why can it go lower?
Yeah.
Because photoelectric absorption occurs at lower energies. And it occurs at lower energies because the lower energies will be matching this energy of the binding energy, or be closer to the binding energy, and therefore is more likely to be absorbed. Whereas if if the incoming energy is far, far bigger than this, then it's going to continue and do other stuff and scatter. Okay, yeah. Got it. Okay, good. Yeah.
So since the outer shell electron, the binding energies of the outer shell electrons are so low, I'm assuming Compton, Compton
Scattering, yeah.
will also happen at lower energies. It's just that there's less.
Yeah, that's right. It's a statistical likelihood as opposed to an absolute rule. Yeah, 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 yeah.
So in the Compton scattering, obviously the X-ray is interacting with a whole bunch of different shells,
Yeah.
different binding energies.
Yeah.
Those regular electrons will all have
Yeah.
different
Yeah.
energy.
Yes, yeah.
So then, does that have any effect?
Well, the reason why we keep saying it's an outer shell electron effect, the first thing to remember is with biological tissue, you don't have that many shells. You know, you've got, you're going to be running out, and if you get past 3, you'll be doing well, you know. So you're not going to have a whole load of different shells. But certainly it's about, because as the binding energy, it's all about, the critical thing is the difference between the binding energy and the energy of the photon. So as you move out from an inner shell to an outer shell, your binding energy goes down. You've got higher energies that go up, and this difference then, once you see a big difference, you're going to get Compton scattering, you know. Yeah, sorry.
So I just want to know what the, obviously this comes back to input, and then inverse square law of energy is entering the
Yeah.
body. So what kind of energy curve and intensity are we looking at as the patient?
What energies are we talking? The energies that you'll be looking at will be similar to what's emitted. The air in between, the inverse square law is really about intensity. You're not so much the energy. So you're not going to have impacted upon the intensity. You will have impacted hugely on the intensity of the X-ray per unit area, but not so much on the energy. Yeah. Yeah.
Yeah, I don't know if I'm going too far ahead here, but what I can assume is the photoelectric absorption is the main cause of DNA damage and the effects on a cell, whereas Compton scattering has less of an effect.
No. You see, this is where you have to be careful. Both are ionizing. They're both equally in the initial ionizing event. They're both doing the same thing. One might be an inner shell, one might be an outer shell, but they're still ionizing. But the Compton scatter, because it's scattering, it can do it again and again and again and again and again. Yeah. I'm not sure if I should be worried about you asking all these questions about Compton scattering or happy. I'm not quite sure. Happy, a bunch of nerds. I hope so. Any other questions? All right, I think that's enough. I think we've got a good basis now. When we get into sort of the next stage of the radiobiology, we'll be in a good position. Hi, hello.
By the way, just talking about like we can talk about cancer and something. So if the photon release an electron and that will got the chemical chain like H2O2 something. Yeah. Around that it will damage our DNA. Yeah. So we just say this that the lower energy will likely to be absorbed. Then, so does that mean the lower energy will be likely to get a cancer for us? Like, will the lower energy will give us a high dose?
Will the lower energy, say that again, will the lower energy...
Will give us a higher dose.
Yeah. Yes.
Yeah, but what if like...
Yeah.
Will this happen at the same time if it's matched for the higher energy will still release an electron?
Yeah, but the higher energy, arguably, is going to, the higher energy, it's a difficult, but energy and dose is a hard one to capture in a single...
The photon with a higher energy will still release an electron.
It will.
And the electron will still cause the chemical thing.
Yes.
As well. So
yeah, it will, but you might get more of that happening with a higher energy, because this higher energy X-ray will continue after it's interacted with the electron. It will continue and do more and more and more interactions.
So what we just said is the scalar photon is more helpful for us.
Yes. Yeah. Good. Thank you. All right.
Just wondering for the photon electron absorption.
Which one?
For the photon electron absorption, we use a lower energy. But for the Compton scatter, we use a higher energy.
Yeah, higher energy.
But I think higher energy was more likely to interact with the K-shell electron. Since the K-shell electron have the largest energy.
Yeah. The key thing is what I said right at the end. The key thing is the difference between the binding energy and the incoming photon. When that's large, you're going to get Compton scattering happening more. Now, for illustration purposes, because the outer binding energies, the L shell, has got a lower binding energy, Compton scatter is more likely to happen at that outer shell electron. It's not that it won't happen at a K shell electron if there's a sufficient difference between the two energies, but it's more likely to happen on outer shell electrons. It's not a hard and fast rule.
It's just like a more favorite environment for the Compton scatter, right?
Yes. Because the Compton scatter, because it's a higher energy, it's more likely to have a big difference between it and the binding energy. And that difference is going to be greatest at the outer shell electrons. But it could happen at the inner shell electron. We're not saying it won't, but it's more likely.
So the Compton scatter prefer the environment which is have different energy difference.
In the X-ray beam. Yeah, yes. It's larger any difference between the binding energy and the incoming X-ray. Yeah, yeah, yeah.
Other question is that the scatter will keep going and then hit other atoms. So is that means that will cause the second scatter?
Does that mean which, sorry? Say that again?
Second scatter.
Compton scatter. What about it? Is that Compton scatter?
Yeah.
Yes. Yeah, when you talk about scattered radiation, what we're talking about is Compton scattered radiation. Yeah. Does that answer your question?
Yeah, I'm just wondering if it will keep going and then that scatter will cause second scatter or...
Yeah, it'll go on. Yeah, it'll go on until it runs out of energy. Yeah. Okay? And sometimes it just emerges from the patient, and then you've got scattered radiation reaching your film or your detector, which is horrible. That's why you use a grid. The reason you got a grid is for Compton scatter. Yeah. Okay, then, righto. Okay. Hi. Yeah. Yeah. Usually out of shell electrons, yeah. Yeah, that's just a product. Just that it's responsible for scattered radiation, that's the key thing. Because the photon, because the difference between the photon energy and the binding energy is so large, it's going to continue, until it runs out of energy. Yeah. No, that's fine. Good, all right, righto. Hi, Justin.
Thanks for my email the other day, by the way.
Oh, that's all right. That's okay. Good.
Quite a long-winded email.
That's all right.
So I had a couple of questions about this and then just one question
Yeah.
assignment. So basically, the only way that a photon ever runs out of energy is by interacting with it. And theoretically, a lot of